Hello, Kia. Hello, Lola. Hello, Lina. Hello, Sarah.
Hi, Doctor.
Nice seeing you connected. So I'll try to be. Who else is connected? Oh, hello, Boston. I'll try to be quick and maybe start sharing right away. And I need to complement what I missed on Friday. And if there are any.
From another laptop.
Okay. Hello. If there are questions to discuss, I'll stay connected after we are done with these slides. Am I sharing the right screen? Do you see the slides?
Yep. Yes.
Okay, very good.
Next assignment.
So here are the subjects for presentations. I will try my best to cover everything tomorrow's in the lab, and I'll also try to share some literature examples from previous years. So if you have some quick questions, please prepare them after we are done with slides. I'll be happy to discuss on the subjects. Okay, here are some recordings from previous years, and I do not like giving homeworks for weekends, but for the sake of starting projects earlier, I'm inviting you maybe to live a little harder week now and make things easier next, closer to the end of semester. So please consider to complete this homework during the coming weekend, and compute density of states and orbitals for each of the model you did for the previous homework. If you have energy and steam, it's better to recompute single point with DFT-PB, but it is a secondary option. If you can do it, good. If you cannot, I'm fine. The main thing to practice building density of states and plotting orbitals. Okay, so back to the subject, and I'll try to squeeze 1.5 lectures to this hour, finishing the last one and then doing new material. So we are studying Hartree-Fock theory, and we need the several basic concepts: Slater determinant, mean field, correlation exchange, and then together they will give Hartree-Fock theory. So we are composing multi-electron function as Slater determinant of single electron functions, and single electron wave functions, single electron orbitals need to keep trace signatures of each other through electron-electron interaction. We are using a concept of partial expectation value when we do average not over all orbitals, but only part of them. And last lecture, I was trying to make an oversimplified exam. Instead of large number of electrons, I focus only on 2. And then 1 electron is the actual electron for which we do an equation, and another electron represents the background charge distribution. For next 15 minutes before I start actual lecture for today, I will use product of 1 electron wave functions without antisymmetry, just for simplification. So in this equation for electronic wave function, I multiply left part, multiply left and right part by this red fragment, red bra number 2 for left and right part. So if you watch on it, so in the middle there is an operator, and on the left there is bra 2, on the right there is bra 2, but in addition there is a not bra, cat. There is a cat number 1, and this cat number 1 will be our unknown function for which we need to set up an equation, for which we already setting up an equation. Then on the we do the same for the right part. So this bra and this cat for number 2 meet each other and make 1, and then we have one electron equation for orbital phi 1. So in the next slides, I'm going to quickly address these 3 terms and then combine them back. So the first is expectation value of kinetic energy, expectation value of electron to nuclear interaction, and partial expectation value of electron-electron interaction. So for kinetic energy, it consists of kinetic energy operator for first electron and second electron. If I do average over the second electron of the first electron kinetic operator, this cancel gives 1, and we still have an operator related to electron number 1. If I have number 2 here, number 2 there, number 2 there, then it will be not an operator anymore. It will be expectation value of the kinetic energy of the second operator. So mathematically, expectation value is a number, and operator is like an operator or a matrix. So just for a second, I'm flipping back one slide. I'm done with the first term. Now I need to cover second and third. So for the second, I am considering an example where I have 2 ions and 2 electrons, and the operator of nuclear to electron attraction does have 4 terms. Attraction of first electron to first and second ion, and attraction of the second electron also to the first and second ion. Each of these 4 terms are here. I'm looking for expectation value of these terms with a bra and cat originating from quantum state of electron number 2. If I'm speaking about electron 1 here, but I'm making an average about state of electron 2 here and there, I am again practicing orthogonality, and it still will be an operator in respect to electron 1. If I have interaction with second nuclei, I do the same, and it still will be an operator. Now I'm going to look on last 2 terms. So here I am looking for operator that depends on second electron in bra and cat of orbital that describes second electron. So I have number 2 here in the operator and here in the function. If I practice this equation, it will bring me to an expectation value, to a number that doesn't follow any quantum commutation. It's just a number that we can treat easily. So I have brackets here. It is a number. If I look on same thing, interaction with second ion, it will again be a number. So out of these 4 terms, 2 of them keep being operators, and 2 of them become numbers after making expectation over the second electron. So I'm going to flip back 2 slides. We are done with first, we are done with second, and now we need to focus on the third. So the third is the shortest one, but most complicated. So we are looking for Coulomb repulsion of first and second electron, but we do find averaging over second electron. So we have two at the beginning, at the end, but in the middle, we have both 2 and 1. So after performing this operation, it will be neither original operator nor a new number. So it will be a hybrid in between of operator and a number. So now I'm going to summarize everything we did before. So here is the first term in the first row, second row, third row. So here we have one operator and one number. Here we have two operators and two numbers. And here we have one hybrid. And this all is in brackets. It acts on unknown function phi1, and by Schrödinger equation, it equals to unknown energy and unknown function phi1. So what I'm going to practice now, I'm going to take all things which are not operators, this one, and this one. And then I'm going to transfer them from left to the right part. So I will take these three terms and I will put them here. I will make a minus sign and put them inside the energy. And then we will keep standard form for Schrödinger equation. On the left, we still will have operators acting on unknown wave function. On the right, we will have unknown eigenenergy. Even if we subtract some numbers, it will be unknown eigenenergy. So we just shifted by the value. And this stuff that I symbolized by red line is expressed by slide here. So I define it as energy tilde, and I subtract these three terms, which are expectation values. So after redefining this tilde energy, I'm obtaining an equation that has operators. So, operator for kinetic energy of electron, operator of electron nuclear attraction only for electron number 1. And then this hybrid operator that corresponds to interaction between of electron 1 that we want to find with electron 2 that we are assumed to know from somewhere. So if we already know orbital for electron number 2, here is an equation that will help us to find orbital for electron number 1. So please try to summarize, to express this statement by your own words. Lola, would you please try to summarize your impression? How would you interpret this equation by your own words?
So I'm just going to talk about the terms, the individual terms. That's what I understand. So the first term is the kinetic energy. The second one is an operator. While the other one, I'm assuming it's number. I'm not sure. But this last term gives us an idea of the second electron. We're trying to find one, so we know about one. I don't know. I just guess.
Okay, good. And the main goal of this equation is to find this phi1 this orbital phi 1 for electron number orbital for electron number 1. So if one knows if phi 2 is known, then this equation allows us to find phi 1, and then by using known phi 2 from here and phi 1 that we find there, we can construct overall wave function that depends on for electron 1 and 2. Let's check. Oh, you did everything great. I didn't find anything wrong. You just try to express this statement from different points of view. Sarah, would you please share your vision of this equation, just how you interpret it?
Well, according to your words, the aim of this equation is finding the phi 1 value, and I guess that this we have some kinetic energy and some operator, and then if the phi 2 is known, then we can find phi 1.
Okay, very good, very good. Yeah, thank you. So let's try maybe one more, and then we'll go for Kia. Would you like to share, just express by your words how you interpret this equation? And Sarah, everything went absolutely perfect, correct. I just want to hear how different individuals express same idea with different words.
Okay, so it's the combination of kinetic energy, and it's the neutron and electron repulsion, I guess. If I'm correct or not. And this one, the force field. So actually, after that, we are looking for the phi 1, the energy of one electron.
Okay, yes. I think we are doing really great. If Boston and Lina do not want to correct us, I'll go forward.
I just want to comment or to check my understanding, if it's possible. So here I find that these equations are interesting because it's as Schrödinger equation, as we know, trying to describe the behavior of these particles. So electron 1 and 2, we can describe their action through if we know the kinetic energy and how they interact with the nuclei, just using the wave function of the second electron for electron 1.
Mm-hmm.
So just we need the phi 2, and of course we will solve for phi 1 and vice versa for the second electron. So I think it's clear for me.
Okay. Yep.
I like the equations.
Yeah, thank you.
Thank you.
Boston, do you approve everything that we discussed?
Yeah, sounds good.
Okay, yeah, thank you. This is sometimes referred as self-consistent field or mean field class of theories. Okay, so done with number 11, going to actual lecture number 12. So I'm going to speak for maybe 10, 20 minutes about so-called variational principle. So if any of you decide to study Hartree-Fock method independently by finding chapters in books or browsing through Wikipedia, the first thing that you will find will be that Hartree-Fock theory is based on variational principle. This is so quick, so short idea that is assumed to be clear for everyone that a lot of textbooks just declare it and skip it. And I thought it is unfair. So let's chat a little bit more about what it is. So please give signs if you ever heard or practiced variational principle in the past, or show no if you didn't.
For me, I think I heard about it, but I forgot.
Okay, Boston, would you like to tell what you remember about variational principle?
The last I remember using it was in classical mechanics when we were solving for cat. So like a
least action principle.
Say again.
Least action principle.
Yeah, I think yes. That sounds very, very familiar. But I remember the problem that was introduced was hanging a wire by both ends and looking at the shape that forms.
Mm-hmm. Okay, brachistochrona.
Yes. Yeah. There you go.
Okay, so can you formulate the principle? And do not hesitate, just by your own words.
Yeah. So again, if I remember right, it's finding. It's varying functions to find the optimal quantities in.
Okay. Good. And what is criterion for when you tell that optimum has been found?
Always minimum energy, I believe.
Yes, exactly. Did everyone heard it? So let me formulate in a very lay language. So if there are options for a natural object to take different configurations, like different interatomic distances or different shapes of electronic clouds, the one that will give minimal energy will be found in actual nature, will be found on experiment. So all systems go to the minimum of energy. Okay? Sounds natural, right? But in a sophisticated language, it is called variational principle. So the way to tell a little bit more math about how nature comes to a minimum, or how we as humans who try to model nature can find this minimum, is by the way, you did already practiced it when we did optimization in the class, right? We just explored several configurations and were finding the one with a minimum. In some sense, we are continuing on the same way, but a little bit more sophisticated. So here are just next 3 slides are I can't do more because it is the only thing that are shown in the books. So first, suppose we need to find a wave function that I will call this psi. Then the energy of the system is computed by the principle of this expectation value. We take bra, we take cat, and we put total energy operator in between. Total energy, which sometimes called Hamiltonian, right? Expectation value. And just in case, so if suppose I didn't compute wave function myself, suppose I go to the store and buy it, and suppose it is too cheap wave function with low quality. So there is no certificate that it is a very good wave function. So just in case I need to do normalization myself. So even if wave function was not normalized, if it was some number n that is not equal to 1, if I divide expectation value of energy by normalization, then I fix this shortcoming. So if I have wave function, I do have a protocol to find total energy, right? Now, if I have several wave functions, I will compute total energy for each of them, and only the one that gives minimal energy will be my favorite. Make sense? Now, if I do not have many wave functions, if I have only one, and I want to slightly sculpture, to shape it to the direction that will decrease the energy. So I will take original wave function 0 and then add a little contribution, and then explore whether this small contribution will increase or decrease total energy. This one sounds too abstract. Let me make a little illustration. So suppose we are speaking about one-dimensional function, although this variational principle will work for any number of dimensions. So suppose our psi naught is this function. Then I add little additions on a side peaks. It's only an example, it's not mathematically rigorous. Then the new function will be like more decorated, like main peak with 2 sub-peaks. This will be my modified wave function. And then the little experiment that I want to do is to find total energy for original wave function and for the wave function that has been perturbed. Ask questions if you disagree with something. Okay, I want to believe that you are fine with this. So we want to compare energies for these configurations. And if I go from pictures to algebraic notation, it is here. So here is the total energy for original wave function, and here is the total energy for modified wave function. Okay. Show minus sign if you disagree. Everyone agrees. And now here is the theorem or principle. If we know for sure that psi naught is absolutely correct wave function for the Hamiltonian H, if it is already minimum ground state of this Hamiltonian, then any modification of this function will increase the energy. If I make an analogy with our one-dimensional geometry optimization, here is like if we are already in the minimum, any motion away from this minimum will increase the energy from E naught to E prime. So if we go from optimal to modified, then energy of R naught will be bigger will be lesser, smaller than energy of R naught plus delta R. So this seems natural, right? And now we are using psi naught and psi naught plus delta psi instead of R, with understanding that psi is complicated shape in space rather than motion along one coordinate. So let me ask Sarah, how would you formulate a variational principle if someone catches you in the if cashier in the store asks you what is variational principle? What would you ask? What would you answer?
I'm not sure about this. I'm not sure.
Any system takes minimum of energy, right?
Yeah.
Yeah, this is a legitimate answer.
Yes.
And anything that brings system from minimum is not favorable.
Okay.
Like if I am laying on a couch watching TV, and anyone asks me to stand up and do something, I say no. It will increase my energy.
Yeah.
Make sense?
Yeah.
So it is my variational principle.
Okay.
Okay. Would you like to express variational principle with your own words? Just try your impression about this principle. What you can say about it?
Yeah. I don't know how to. Let me think. Maybe it's not.
If you already have the wave function that gives us minimum of energy, would you would change of this wave function increase or decrease energy?
It will increase the energy.
Yep. So you did answer. You know variational principle. You were just hesitating to say it, but absolutely correct. Thank you.
Because I don't know the right answer.
Now you can. Now you can.
Okay.
Lola, would you try?
So variational principle is the principle that explains the concept of a system wanting to be at the minimal energy as much as possible.
Mm-hmm. Yep. Very good. Very good. And any attempt to bring system away from minimum means increasing of the energy, nothing else.
Okay.
Okay. Whew. So why do we need it? Why do we need it in this class and in this lecture and in this subject? So there is no doubt that we need to find correct wave function, right? And we are looking for multi-electron wave function that depends on 1, 2, and so forth electrons. So we need to vary, to modify the wave function to such way that it will come to the minimum of energy, right? No doubt. And here, by the way, now you all are certified experts in variational principle. Absolutely, there is nothing more in that. It's therefore it is skipped in textbooks. They just write one line because every human knows what is minimum of energy, right? So, but right now we need to apply to our course, and there is a practical question: which parameters I want to vary. Vary means change. What do I want to change in the wave function in order to minimize it? If someone knows the answer, please speak up. But I'm not expecting you to. You may guess if you.
Would be the amplitude.
Well, if we normalize anyway wave function, then amplitude, if you multiply everything by constant or divide by constant, wave function doesn't change.
Mhm.
We can try to make it imbalance, make one side bigger, another lower, something like that. But we already have some solid foundation. We know that if one electronic wave functions are known, are available, then we can multiply them in a certain way and construct multi-electron wave function. So what if I have these balloons, this one electron orbitals, and that I try to change their shapes and then combine them together into multi-electron wave function and see if changing a shape of one electronic wave function will affect overall energy of multi-electron wave function. So I'm going to come to this idea again and express it in different words. Whew. So,
Doctor, do you mean that choosing the available states which give the minimum energy?
yes.
Or modifying maybe?
So to modify, just to understand by human brain how to modify multi-electron wave function is too complicated.
Mhm.
But we can quite easily understand how to modify one electron wave function because we can draw orbitals, right?
Yes.
And if we change shape of the orbital, first orbital, second orbital, and then combine them into wave function and check whether modification of one electronic components will change energy of the overall system. Okay. There is one statement that is not naturally self-explanatory, that one can solve only one electron equation, get many orbitals out of them, and all these orbitals will be used to compose the multi-electronic wave function, as in our Bohr principle. Whew. And here is my favorite slide. Although it is very brief, very short, I'm going to speak about it at least for 10 minutes. And it also, you will see it relates to the one of you who selected to present about basis set. So maybe if there are volunteers to explain what you see on this first equation, please speak. So Boston, would you like to try?
So is that a linear combination of wave functions?
Mm-hmm.
And yeah, that's about where I'm at.
Okay, good. Lina?
Here as so phi is the wave function in terms of the atomic summation of atomic orbitals, and So we can see there's a coefficient.
Mm-hmm.
Each term will have a coefficient.
Very good. Very good.
This coefficient is important for some reason.
Mm-hmm.
Variation of principle.
Oh, okay. That means you already know what will follow.
I'm remembering some things.
So, if you remember our last lab, maybe for this titanium hydroxide, you remember that there were, for example, HOMO orbital was looking like p orbitals on oxygens, right? And they were colored by red and green. Does it look similar to the orbitals that you've got with Gauss U for HOMO of titanium hydroxide? Approximately? Do you recognize it? So thank you. So it was molecular orbital equals 24, right? So this number 24 is here, J. So molecular orbital number J. The index MO tells that it is molecular orbital rather than atomic. Now, what are these chi functions? In specific example of our last lab, K, can you try to explain what is this chi and make connection with the image that I did draw?
If I'm not wrong, then.
Huh? Please.
Oh, what happened? Okay. If I'm not wrong, then it's also a it's also wave function.
Molecular or atomic?
Electron, I guess.
Yes, we are speaking about electron wave functions, but now on this slide we are speaking about two types of wave functions or orbitals, molecular or atomic.
I think molecular.
You can read. So this. So the letter phi stands for molecular, right? And this chi.
Okay.
Atomic, right?
Exactly.
Okay.
Also written there. Oh God.
Okay.
Oh my God.
Now,
Okay.
a question to Lola. Would you please try to interpret the symbol R capital sub I on the example of this from our last lab? Like in this image, what is R sub I?
I know R is position.
So if lowercase r is position of electron and uppercase r is position of ion, right?
Okay.
So and we have summation over I, so there are different ions. So which ions are involved in formation of molecular orbital in this molecular orbital number 24? Which atoms or which ions are active? Like, is titanium active?
The OH?
O, only O, right? Atoms O, oxygen, right?
Okay.
So if we want to build to construct same equation for this orbital, I would write. Thank you. You were correct.
Why is it only O actually?
Because it is p orbital. On hydrogen, there are no p orbitals.
Okay.
So if we tell MO equals 24 for our titanium hydroxide of R, and then we can say there will be 4 terms. So p orbital, let's say p means L equal 1. P orbital on the oxygen number 1, O1, close bracket, plus atomic orbital with angular momentum 1, p orbital on minus R on the oxygen number 2, plus I apologize. I missed my own notations. I'll quickly fix it. Yeah. I shouldn't do it. I should use the letter chi. Whew. Sorry for any confusion. So chi L equals 1 for on the oxygen number 3, or 3, plus chi L equals 1 on minus position of oxygen number 4. So we have 4 p orbitals. 4 atomic p orbitals are composed together to build one molecular orbital, right? And what is specific to be to avoid ambiguity, one needs to have some coefficients, maybe like 0.25, 0.25, 0.25. I'm giving it only as an example. So all these atomic orbitals are coming together with some proportionality coefficient. And this stuff that I labeled as 0.25 is this C, right? So what is important to notice that this C coefficient has 2 indices. One index relates to molecular orbital, and another index relates to atomic orbital. So it shows how to compose molecular orbital number J out of atomic orbital number A. And since there are so many different atomic orbitals, we need to make summation over all orbitals A and over all atoms, all ions in the molecule. Since the example of this titanium hydroxide has 9 atoms, there will be additional 5 terms, but they basically will be zeros because we do not see anything on titanium or hydrogen. So there will be some 0 terms. So today we came closer to the definition of molecular orbital. It can be expressed as some linear combination of atomic orbitals. And under the letter A, I summarize all 4 quantum numbers of one atomic orbital: principal, orbital, magnetic, and spin. Because otherwise I will be tired to put all these indices here. Okay. Another slide which some of you may consider as main slide for this lecture, or maybe for the whole chapter. So let me invite you to follow this set of symbols. So the set of symbols is a protocol how Gaussian software is working towards obtaining total energy. First, we start with positions of ions, right? Either drawing by hand or optimizing or borrowing it somewhere. Now, for each model, for each ion, we do have set of atomic orbitals. We know them, we take them as hydrogen wave functions, S, P, D orbital, right? Now, we take somewhere expansion coefficients, in which proportions we take atomic orbitals to build molecular orbitals. Then we build molecular orbitals, and then we combine them together according to product or Slater determinant to construct multi-electronic wave function. And then as soon as we have multi-electronic wave function, we build total energy, and we tell whether it was wrong or right thing. By the way, before we go forward, let me
Control Z.
I know, but my keyboard is not reliable. And one more undo. Yes. So this C sub C uppercase A lowercase j is stored in the .fchk, in the form check file that you are using to build orbitals. And this phi sub j molecular orbital is what you store in the cube file. Okay. So here is a thread, and here I'm asking a question to myself. If the main subject of today's meeting was variational principle, if I want to vary something until I get minimum of total energy, what I can vary in this thread, in this line? Can I vary atomic positions? Generally, yes, but not in the method. We do single point calculation. We stop, we nail them down. Can I change atomic orbitals?
No.
No, they were computed by Schrödinger in 1927, once forever. Can we vary expansion coefficients?
Yes.
Yes. And then the rest will roll over naturally. So basically, Hartree-Fock theory is a theory of varying molecular orbital expansion coefficients until we get minimum of total energy. Make sense? So by now you know all principles, and the rest will be details for practical implementation. So in some sense, the computational procedure to vary, which means change values of this C coefficients, is similar to procedure for optimizing geometry. When we optimize geometry, we have several Cartesian dimensions for each ion, right? And we move each ion. Here, we have so many C sub A coefficients, and we will use each of them as a dimensionality, as an analog of Cartesian projection of ions, but we will change value of these projections as a browsing in multidimensional space of these expansion coefficients. Okay. Whew. I think we do not think that we are done with the lecture, but we are done with main idea, and the change of this expansion coefficient will be repeated in an algorithmic way until we reach minimum of the total energy. And the values of molecular orbital expansion coefficients should consist to each other. Therefore, it's called self-consistent procedure. In order to implement it, in order to find orbitals, we will need to solve to find Fock operator and find one electron Fock equation. So this letter F and this one electron Fock equation is the stuff that we were going over in the first 15 minutes of today's lecture. I'm going to flip back about 20 slides. This equation. This is Fock equation, and in many textbooks, instead of details, they just write it as F phi equals E phi. And under F, one understands this stuff. Self-consistent analog of Hamiltonian. I see some of you are yelling, which means it started being boring or too complicated. So I know if some of you need to disconnect, I do not have right to ask you to stay longer, but I won't.
Maybe,
So,
Professor, because of my eye problem, I am not able to see that color.
yellow color? Okay.
Yes.
I can do different color. By the way, most famous scientists in spectroscopy were not able to recognize colors. It's no historical fact. So it's so if anyone needs to disconnect, I cannot stop you from this. But I have plans for showing something for another about 5 to 10 minutes. So please show if you are okay or if you are against. Okay. So what I'm going to show, I need to touch the way how total energy is computed. So I need to touch the last stage of this thread, how we convert multi-electron wave function into the total energy. And there will be some underwater stones, some hidden barriers that I want to make you aware of. Of course, computer does all calculations for us, but we need to know which difficulty it faces in order to adequately describe which problems we are solving. So I'm going to focus on this last stage of converting multi-electron wave function into total energy. So I will take again 2 electron thing, but now I do not want to be approximate. I want to use exact Slater determinant. So if I already obtained 2 molecular orbitals, phi 1 for electron 1 and phi 2 for electron 2, then I have to combine them as antisymmetric product. And I use it as bra and cat. Cat without stars and bra with stars. In between, I will process only electron repulsion because it is the tricky term. The rest of the terms are easy. If you one can write for several pages of equations, but they are not they do not have challenges. If one does good faith work, meticulously writing them line by line, everything is clear. But this one is really challenging, and I want you to recognize it, and later we will need it. So before I go to this equation, I'm going to entertain you with some colorful figures. And you may know it if you were glancing over the slides. So in the figures, I will illustrate all of the equations, all of the objects that are on the plate right now. So I will show the first part of antisymmetric wave function. I will show second part of antisymmetric wave function. I will show overall wave function. Then I will show what would happen if we skip antisymmetrization. Enough. So you may have seen it before, plus and minus, and this shows just product, electron 1 of x1 times electron 2 of x2. Supposing that it is a particle in the box and they take first and second eigenstate. Now, if I swap the order, if I do phi 1 for electron 2 and phi 2 for electron 1, then you see the figure flips. So now it is extended not in vertical but in horizontal. And if you want to compose antisymmetric wave function, it will look in this way, right? So nodal line will go along main diagonal, plus minus. And if one swaps the sign, then it will be the same function, just with split sign. Now, you have already seen this illustration. Now, how can we deal with Coulomb interaction? Coulomb interaction is 1 divided by distance between electrons. If there are 2 one-dimensional electrons, this function looks like 1 over r, right? 1 over this difference. You know this function. And when distance between them equals 0, then it takes infinite value, plus or minus infinite. Which means interaction has infinite values. And here we have plus, here we have minus. This would be strange. If we swap electrons, sign is changing, it will not happen. Therefore, one is taken, one needs to take absolute value. So Coulombic repulsion depends only on distance, not on the order. And here, this is illustrated here. It is a function that has maximum when distance equals 0. So it equals infinity. Now, if I want to practice expectation value of the Coulombic attraction with Hartree product, with a product of wave function without antisymmetrization. So here is the wave function squared, and here I practice this wave function, divide by this Coulomb repulsion, and integrate over 2 variables. So if I practice this multiplication before integration, it will have infinite value on the main diagonal. And if I perform integration, the answer will be infinite, which means repulsion of 2 electrons will have infinite value. And you know, infinite value means it either does not exist in nature or it is in the it is about to explode. So something is going wrong. Now, if instead of product, I take this antisymmetric wave function, which has, please follow me in noticing that on the main diagonal of this thing, there is 0. If if here is the wave function, and if I take wave function absolute value squared, which is needed for matrix element, still on the main diagonal it will be 0. And if I convolute this stuff with Coulomb kernel, it will be the infinity that comes on the that Coulomb has on the main diagonal is compensated by 0 of the antisymmetric wave function that has on the main diagonal. Therefore, the result of this integration will be finite. So repulsion of 2 electrons will have finite value. So 2 electrons, although they do not like each other, but they can survive. Like 2 neighbors who hate each other still can use the same elevator without exploding. Right? Now, after ending of this fun demonstration, I will bring it back to language of equations. So, what if I take product, and Coulombic term? So predominantly wrong thing that will give infinity. I will call it first term of the Slater determinant matrix element. So bra and cat, each electron is on its place. Notice it is positive, right? It has positive value. Now let's take the cross term. So if I take this stuff and this stuff, cross term, it will gain minus sign from the antisymmetry. So here we have 1, 1, 2, 2, and here no, I need the next one. Yes. So 1, 1, 2, 2, and here we have 1, 1, and 2, 2. We flip the order. And then this term will be completely negative. Right? So when computing overall energy of electron repulsion, we will have 2 terms. One term is positive, another is negative. If you have only positive term, it will be unphysical. But if we add negative term, they will approximately compensate each other and add stability to the system. So when the energy is not as high, it is more stable. So there is a specific language, there are specific terms to address this term number 1 and term number 2. Term number 1 is called direct, and term number 2 is called exchange, because we swap order of electrons. So I think that's it. The rest are the words. So the antisymmetry wave function is mandatory needed for Hartree-Fock total energy because it brings exchange Coulomb interaction. Exchange Coulomb interaction stabilizes system of electrons and allows chemical molecules to exist. Historically, Hartree, the scientist Hartree, forgot about this antisymmetry. He created Hartree theory, but it was predicting that any molecule in the nature must explode. And then Fock came and said, hey, you have forgotten antisymmetry, let's add it. And then everything became stable. So all hard job was done by Hartree, and Fock just brought to the attention that there should be antisymmetry stabilization of exchange. Enough. Thank you for investing additional 11 minutes into the thing. And I'm really happy that we covered this material. Now we're up to date with everything. So meeting is done. Everyone is welcome to disconnect. I'll stay here just to answer questions if any.